Hey everybody. Today we're talking about the moments of probability distributions. We're going to focus on discrete distributions in this vid, but everything carries over directly to the continuous case, just with summations replaced with integrals. So we're in a situation fundamentally where we have some random variable and we're trying to understand its shape just a little bit better. We'd like to be able to talk about its center, its spread, its asymmetry, and its tailedness. How fat are the tails of that distribution. And we do that using the quantities mean, variance, skewness, and kurtosis. And if you look at those mathematical definitions on the left here, you see a little bit of a pattern. We're doing expected values, and they're fundamentally powers of x that are inside there, or polynomials that are involving powers of x. So we'd like to be able to compute those. We'd like to be able to do that efficiently and have some settled language for doing so. So here's where we start. The kth moment of a probability distribution about the value x equals c is defined to be the expected value of x minus c to the kth power. And so if you compare the indented thing I have here to what we saw in the last slide, you see the direct similarity when k equals 2, 3, and 4. When c equals mu, which is the most useful case, the thing we usually care about, we call this the kth central moment rather than the moment about x equals mu. And when c equals 0, which tends to be the one that's easiest to compute, we call that the kth raw moment. The first central moment of any distribution is always 0. So we don't tend to talk about the expected value of x minus mu, because that's just mu minus mu. And so we only ever really look at the first raw moment, that is to say the moment about 0. Before we go any further, let's do an example. Compute the first raw moment and second central moment of the random variable that you see here. As usual with my examples, I recommend that you pause, try this on your own before advancing. So really this is just computation. The first raw moment is just the expected value, so we're going to take each of the individual values of x, multiply by their respective probabilities, add everything up. We get about 3.60 in this case. If we were to do this, draw from this random variable many times, on average, we expect to get 3.60. The second central moment, or the variance, again, just computation. You take each of the individual x values, you subtract off the mean from each one, square and then multiply by the probability, f of x. Add all those things up, you get the second central moment, the variance. It's about 0.84. The standard deviation would be the square root of that, by the way. When k is at least 2, the kth central moment has different units than the random variable x, because inside of that expected value, you're taking a power of x, basically. And so that makes things less interpretable, and so for that reason, we often look at the kth standardized moment, taking that same expectation, but then dividing by sigma to the k. And that gets us back onto the scale of the original random variable. If you plug in k equals 3 or 4 into that expression, you just get the definitions of skewness and kurtosis, respectively. We already talked about why we don't worry about k equals 1 here. We just look at the first raw moment. But what about k equals 2? Well, it turns out the second standardized moment is always equal to 1, because in that situation, both the numerator and the denominator of this expression are the same. They're both just the variance. And so for that reason, instead of talking about the second standardized moment, instead we just take the square root of that expectation to get us back onto that scale of the random variable. That's the standard deviation. Let's continue on with this example that we started with a little bit ago. Let's find the third standardized moment, or skewness, of this random variable. This is really just a computation, plug and chug. You do exactly the same computation as you did for variance a little bit ago, but now instead of a square inside of that summation, it's a third power. The other difference is that when we're done with that summation, we divide by the third power of the standard deviation. That is to say, the variance to the 3/2 power. In this case, we get about negative 0.31. In practice, this isn't generally how we compute skewness, or much less kurtosis, or higher central moments. Rather, we do that by leveraging the fact that that expected value of x minus mu to the k can be written as a sum of multiples of the various raw moments, and those raw moments are in general much easier to compute. So for instance, just looking at variance, the expected value of x minus mu squared, We can FOIL out that x minus mu squared and then break up that expected value into three pieces using the linearity of expectation to get the expected value of x squared minus the expected value of x quantity squared. Similarly, we can do that for skewness, kurtosis, any higher order centralized moment that we're interested in. Let's see how this works out in practice using that same distribution as before. Find the third standardized moment of x using its raw moments, and that'll allow us to get the skewness, confirming the calculation that we had a little bit ago. So the calculations of the raw moments are all more or less identical. We basically do the same calculation that we did for the expected value of x, just instead of multiplying the values by their probabilities, we multiply the squares of the values or the cubes of the values times their probabilities. And in this case, we get an expected value of 3.60, like we knew. We get the expected value of x squared is about 13.80, and the expected value of x cubed is about 55.49. So now we can get the third central moment by plugging into that formula that we had a couple slides ago. The expected value of x cubed minus 3 times mu times the expected value of x squared plus 2 times the expected value of x quantity squared. When we do out all that arithmetic, we get about negative 0.24. If we then divide that by the square root of the variance taken to the third power, we get about negative 0.31, same as what we found earlier.